So I couldn't be happier to be introducing this year's distinguished lecturer, who is Dr. Shananda Basu, who's very, very well known to this community. So Shananda got her PhD in Calcutta sometime, a little while ago, and very quickly, that's a way to put it, and very, very quickly transitioned to our community here, and she now works at BC, but she's worked at BU and AFRL and NRL, and has accumulated an extraordinarily long and accomplished list of publications and work in the area of radio and space physics. So widely published. I think even if you don't recognize Shananda's face, you know her name very well. And of course, she's known to us because of the tremendous service that she performed as the director of the astronomy program for about 10 years, ending about 10 years ago. So many of us received, our first research grants from Shananda. I certainly did. I probably received my first declination too, but I've gotten over it. And so I'm really looking forward to this talk. I know we all are, and I won't take any more of Shananda's time. So
thank you.
Please.
Thank you. Well, what can I say? I just had never expected this to happen in my lifetime. So here I am sitting on the stage. I can't stand too well, so I hope you'll pardon me for that. This is working, right? The microphone is working. Yes. Okay. And unfortunately, everything is kind of happy in one way and bitter in another. And this is particularly so. Shanti, that you know equally well, my husband, Shananda Basu, he passed away on the 16th of April, 2013. So that's just exactly 10 weeks ago. And his friends and colleagues at Boston College wrote a very fine obituary for him. And so I just point out, if any of you are interested, since I know he has many friends in this community, then that was in the SBA newsletter, and it was dated May 1, 2013. Okay, to go on with, and everything is a partnership for us. But this is, when I sat and thought about this talk, how am I going to structure it? And maybe this wasn't the talk you had imagined that I would be giving, but under the circumstances, this is the only kind of talk I could come up with. And so I hope you'll pardon me if it isn't what you expected. So I just wrote about our lives together. And we had a 52-year marriage, and so that's a lot to get over. And everything happened under Shanti's watch, because I was 20 when I got married and just had an undergraduate degree under my belt. And so my graduate student years were also with Shanti, helping me through every phase of it. Okay, so the way I thought I'd structure my talk is first to talk of my graduate student years. The little inset photograph was taken by a Boston Globe photographer and put into the newspaper the next day. I guess a sari-wearing woman getting a graduate degree in physics was rare enough that I made it to the Boston Globe. Anyway, and so I did my master's in the US at Boston University, and I made an awesome discovery that I'll talk to you about. And then I did my PhD in India. It was very important that we live with our mothers. We had 2 widowed mothers, and we were only children on both sides, so we just had a lot of responsibilities back home. So we decided to go back to India, where I did my PhD, but also more on that later. And then Shanti had to build the beacon receiver. You'll understand these phases as I get into my talk. So it was like very much CEDAR-like, that you first build your instrument, then you take data with it, then you analyze the data and write papers. And then I did my NRC means, of course, in the United States. So I did my postdoc in the United States and lived in this country from then on. And then I go on to my first phase of my partnership with Shanti, and then that's doing research together. And then I spent a decade at NSF and managed the aeronomy and CEDAR programs. And then I'm sure I'm not going to get to the second partnership phase, but that's all about our work with magnetic storms. But let's see how far we can get along this line. This is from my master's thesis, and it didn't, the diagrams then weren't the crisp digital kind that we did, that we have nowadays. And so this was on high latitude scintillations by receiving signals from artificial satellites. And so this was a discovery phase. Whatever we did was publishable because no one had done it before. So there were no artificial satellites. And one of the first studies of high latitude scintillations using satellites was made in Boston by Jules Ahrens and his group. And believe it or not, the satellite I used was the Soviet satellite Cosmos 1. There are Cosmos 2500 at this time and counting. So it makes me seem like a fossil, and I have to be present in front of you to prove otherwise. And the American Satellite Transit 4A were used. And let me just, where did I put the pointer? Oh, this is it. This is, and it was megacycles per second and not megahertz at that time, okay? So the data was taken in Sagamore Hill, Massachusetts. That's somewhat north of Boston, about 40 or so miles. And this is 3 minutes of data. The satellite, of course, moved about 7 kilometers per second. So it moved very fast. And it rose on one horizon and set in the other. And so this is the 20 megacycles data. And I'm going to say megahertz because I'm going to always then get bothered by it. So 20 megahertz and 40 megahertz. And this was data was from April 12, 1962. And you can see some parameters at 16.7 EST. That's local time is just at around midnight. This was the longitude and this was the latitude. So obviously the satellite rose to the south of the station and set to the north. And these are the transmitter pulses, and this is the Faraday rotation of the plane of polarization. And then you see the very fast fluctuations. So these are superimposed on the Faraday rotations, and that's what we call scintillation. And this is the Pmax, that is the highest it rises, and this is Pmin. But now we wouldn't even dream of using such low frequencies because that creates a lot of propagation effects. As you can see, at 20 megahertz, you can hardly even count the Faraday fadings because the scintillation is so large that it just confuses everything. And so now we mostly use 250 megahertz for any communications work. And so this was part of my master's thesis, and this was 1963. So that's my 50 years. I don't round up or round down or anything. My advisor was Gerald Hawkins, better known as writing the book Stonehenge Decoded. So he had a lot of other interests. And this was, my thesis was published in JATP in 1964. And I'd also done a couple of papers with Dr. Ahrens at that time because I also worked summers over there. And just to show you for the students who perhaps isn't as familiar with scintillations, and to maybe please our chairman here, who's a radio scientist and keeps saying that we need more radio scientists in the field. So anyway, this is how we get scintillations. If you have vertical a plane wave coming on to the top of the ionosphere or atmosphere, however you want to say it, it's all ionosphere there, and that is the top of the atmosphere. And then you have an irregular layer which is placed at about H max, because otherwise you're not going to see very much scintillations. And then the emerging wave front is all has phase corrugations on it, and that phase then from that phase fluctuations develops amplitude fluctuations that you can observe on the ground if there's relative motion between the irregularities and the ground, which of course is static. So, and I'm saying that for the people who really want to know more about scintillation, please see the CEDAR tutorial in 2003, again 10 years ago, which was given by Shananda Basu. So, so you can learn more. I cheated a little bit and took a view graph from a much later period to show you what the impacts of scintillation are, because these are the impacts that are most notable at this time. And that's, we know that UHF, that is anything above 300, except the Air Force has its own rules and calls 250 megahertz UHF. But so any of the regional communication outages for extended periods, namely ours, increased global positioning satellite navigation errors. Of course, in the 60s, there were no global positioning satellites. And then degraded high-frequency radio communication, which is a real problem for pilots flying the polar route now. And so it has become a real serious space weather issue. Well, my unique, or whatever I call it, discovery, or awesome discovery, I thought the students like a term awesome. So, anyway, the advantage of the scintillation technique is the simplicity of the receiving system that can be used when the source is a satellite, because you have high signal strength. Thus, this technique is suitable for developing countries, because I was going to go back to India, and there wasn't anything I could do that was really fancy. Well, little did I know what faced me when I went back to India. Expectation was that I would teach undergraduate physics at a college for women. I mean, I'm a woman. Why should I want anything higher than this? And please note that I'm not saying there's anything wrong about teaching undergraduate physics. In fact, it's one of our, we should do this. All of us need to do it. But I'm saying if I want to do something else, a man can do it, so why can't I? So research in radio physics was only possible at Calcutta University, and where Shanti was on the faculty. Well, the head of the department there said he wouldn't admit a woman. And he was completely, that's the ruling. You can't have any exceptions. Well, I was equally adamant that I would do research. So we decided to have a baby while waiting for an opening. I mean, truly, you can't just sit and wait and not do anything. So, so 6 months after the birth of our son, we found another university in Calcutta called Jadavpur, where the head of the telecommunication engineering was more open-minded. And so I started work there with a junior fellowship from the University Grants Commission in June 1965. A group of one with the expectation that Shanti would provide guidance. And I haven't stopped doing research since. So I'm just saying that it's so important to follow your passion and do what you would love to do. because I could have been a very embittered teacher, not doing a good job because I would feel that this is not really what I wanted to do. So anyway, things worked out for me. And as I said, this is the discovery phase. Everything gets published. So these were satellite signals being received at Jadavpur and at Calcutta. And in the low latitudes, there's a very interesting region that you see to the north of you, where the ray path becomes perpendicular to the magnetic field. And so the propagation angle is 90 degrees. And there can be no rotation, or almost no rotation, between the ordinary and extraordinary modes. And there are a lot of issues that develop, and I'll mention some of them. So this is at 20 megahertz, and at 40 megahertz, this is, they got a similar measurement at Calcutta, Shanti and his first graduate student. Now, these two satellites, BEB and BEC, BEB and BEC, were very well known in the satellite community. Dr. Ahrens actually put together a community called the Joint Satellite Studies Group, which had a lot of international partners. As I said, that they were all in many different countries, not all developing, but many developing countries. And they could do these measurements and find out a lot of information on the local ionospheres. And so some of the results that came out was the mapping of the latitude variation of total electron content. And these are in the 4 different seasons. So that's in the, and the dates are written with the date first, the month second. So this is the British way of writing dates. So this is in the spring and the fall. Then I think this is the winter, and this is the summer, the lowest total content in the summer. And what I forgot to tell you was that India is under the equatorial anomaly. So the equatorial anomaly could be mapped out by doing the TEC measurements and its variability with season and with magnetic activity. Okay. I, on the other hand, had no graduate student, and I mean, it was very difficult for me to do a lot of measurements. So what I did instead was to do more computationally heavy kinds of things. And so I looked at the magneto-ionic mode coupling that would result from being in the so close to the transverse region. And here is the locus of the transverse point, right? Locus of the transverse point as it goes up in the ionosphere as you move away from the station. And this shows that this is between 2 forward-going waves, mind you, both ordinary and extraordinary. It's not what mostly the ionoson people think in terms of a upgoing and a downgoing wave. Anyhow, so you can get error of about 15 or so % at night. That's the nighttime region, the outer region, and the daytime region is within the crosshatched region. So, and the daytime errors are smaller. So that's telling you that if you have a lot of total content, and later on we never use such low frequencies to work with, and so these errors are not at all that difficult to handle. So the summary of scientific studies in space weather at Calcutta during 1965 to 1975. Well, as I just mentioned, Calcutta is located under the northern crest of the equatorial anomaly. The total electron content variation with satellites BEB and BEC measured at Haringhatta, that's the field site of Calcutta University, could map the equatorial anomaly and its variations with season and magnetic activity. And then the magneto-ionic mode coupling and refraction correction, these studies were also performed at Jadavpur University. And as I said, that I was lucky that I had 4 chapters in my PhD thesis, and all 4 were publications in JGR. You know, these 3 and this one. So I was very proud. Even though I did my degree in Calcutta, I wanted my thesis to be of international standard. And actually, Shanti's student Dasgupta had the same 4 papers. So I don't know if he had 4 chapters, though. Anyway, the Dr. Jules Ahrens came to Calcutta in 1969, and this was a big deal for at the field site. And Shanti's professor, Professor Dasgupta, he was there, and Shanti's first graduate student is also Dasgupta. And here is Shanti, looking kind of debonair and jaunty, because he had brought Dr. Ahrens over there. So this was in February 1969. That may ring a bell. Oh, well, before we go to that, this is Dr. Ahrens only took museum quality pictures. He had one person that shows in Boston and New York and Paris, so he was an absolutely talented photographer. Anyway, he doesn't take pictures of people's children, but he did take a picture of Shushanto, and Shushanto was not pleased at all, and children will put you in your place, as you know. He looked so sour, and well, his father was speaking in a language he didn't understand. He didn't know a word of English at that point. And his mother was off to the 3rd International Symposium on Equatorial Astronomy in Ahmedabad. So, by the way, Shanti's head of the department was so strange. He said he hadn't been invited properly, so no one from his group could attend that meeting. So I said, hey, I don't work for your boss. I'll walk to this place if I have to. This is two nights train ride to get there, and that's what we were allowed as grad students, is train fares. And frankly, I didn't have the money to buy an airplane ticket. So, so there I was, and this is the only autograph I've ever taken from any human being. And Professor Chapman was, my lucky break. He was standing alone, and I didn't have a single piece of paper, but I had just bought this picture of Professor Chapman and Sarabhai. I'll come to him. And so I asked Professor Chapman if he would just autograph his picture. And he's a very kindly gentleman, and of course he agreed. And so, I was delighted, and my friend who was with me did me the honor of taking that picture while I was getting his autograph. So anyway, these 2 pictures are always on my table, because if you have to have a role model, Professor Chapman is one of the best. And I showed this picture at Ethiopia, and Rich was there, and of course he told me that the content of my talk was 0, and I'm sorry for that. So this time I don't know if that'll make this picture will make this talk 0 or not, that I don't know. But anyhow, hopefully it will have some content. So because we were able to have the first Chapman conference, I like to digress, I'm sorry, but the first Chapman conference in Africa, in our field, was held in Ethiopia, and that was in November 2012. So that is just last year. And I showed this picture over there because I wanted to tell them that Professor Chapman was a very noted solar terrestrial physicist, And I had met Chapman, so again, that I'm not, while that may sound terrible, but I was, at least I had the pleasure of doing it, and he wasn't, he didn't die that long ago that there could be no one who was living who met him. So of course in this audience there must be many people who had met Chapman personally, but at the Ethiopia meeting there was just Sandro Radicella who put up his hand when I said that who else has met Chapman. So anyway, and it was great, but I wanted to pay Tim Fuller-Rowell our thanks, because he worked like crazy on this one, and then there was another meeting 5 years ago, but I'll come to the earlier meeting later. So to move on, so we finished, so-called finished, the first 2 phases. In case you want to find out where you are in this unending saga, this is now we're coming back to the United States, and this is my postdoc now. Because again, when I tried for a job, Professor Parr was still the head of the department, and he said, while I'm the head of the department, then it was a research student. Now it became, I'm not going to have a woman on the faculty while I'm the head of the department. Well, I wished him a long life, and I came to the United States. So again, I was really, really lucky. So I've had my lucky breaks, okay, many of them. Otherwise, and I had 2 great mentors. One was Jules Ahrens, I called him my ground-based mentor, and Bill Hansen, whom I called my space-based mentor. And it's really very important, particularly for women at that time, where there were so few other women, to really to have mentors who would help you to make the right choices. So, but actually he had sent me the OGO 6. I don't know if anyone can recognize this, but this is a sketch of Bill's face, and it was on the thank you note that his wife Anne sent around to all his friends after his death, just as a recognizing the things that other people had done, sent cards, flowers, and so forth. So anyhow, and in that note she said that Bill considered you, well, both of us, real personal friends, and I've still treasured that note and kept it. And so that's where I got that from. So he had sent me 30 pounds of data, literally, because I didn't even have a microfiche reader at the university. But I had met him in 1972 at Dallas, and asked him a string of questions. And he said, look, Shananda, no one knows the answers, but you know the questions. So when I have the data, I'm going to send it all to you, and you can find your own answers. So he sent me this OGO 6 data, and from that I tried to every page, I had to manually analyze, and I came up with this longitudinal variation of scintillations. And then this was new, by the way. No one had talked about a longitudinal variation of scintillations. And I know Chuck Reno is looking at me. When I first gave that presentation, Chuck was in the audience. And there was Ed Freemau, Chuck Reno, Sid Osikoff, Leon Whitwer. And Dr. Ahrens wouldn't hear of me not giving that talk. So I came, this allowed me to write a NRC postdoc proposal, and it also gave me a ready-made paper to give a talk on. And the real heavyweights in the field were all sitting there in front of me, and I had to give that talk. I mean, he doesn't remember. It wasn't a big deal for him. but it was really a big deal for me. Hey, how am I doing on time?
20 minutes, 25?
Hmm?
25 minutes?
Oh, okay. Thank you. So I should hurry. And this, if I go to the next one, and I had to put in Chuck Reno's equation, of course, knowing that he would come. Every orbit was like this. You had the delta n over n, which is here, for 3 seconds of data, and then you had ignore the middle panel, and then here you had the density, the ionospheric density, and this was all at 400 kilometers. So for this part of the OGO 6 orbits, they were just perfect for trying to do scintillation, model scintillations from the in situ data. I want you to understand that in situ data is not scintillations. You can use the in situ data to model scintillations. And at some parts of the orbit, part of the longitude, you had these huge delta n's. So you knew something different was happening in those orbits. And this is like at 36 west, 10 west, and so forth, where you saw this kind of behavior. So we find that over Africa, you have the maximums. This is occurrence, mind you, 100% occurrence of scintillations greater than 4.5 dB. I converted the S4 to dB so that this is basically contours of electron density deviation of 10 to the 10 or whatever. Anyway, I can't see. I think it's 10 to the 10 per meter cubed. So the occurrence contours of 140 megahertz scintillation during 19 to 23 MLT for November-December period were derived. A pronounced longitude variation of the scintillation belt width and the occurrence was obtained in agreement with observations. Then in that paper in radio science, I went back and did comparisons with the ground stations like Huancayo and Ascension and so forth. Okay, I want to make the point that this was our first exposure to in situ data and was followed by work with AED, AEE, and DE2, none of which I can present today. That's like all plasma structuring. It's not really space weather. So and I call it exciting is because it really opened the door, for me at least. That was the most exciting work I found, was to combine ground with space and bring in other techniques like optics or radar. So this was really, as I say, very exciting whole branch that I was able to get involved in after my postdoc. And that is, after all, what the postdoc should do, is open up other avenues for you to work in, and away from perhaps what you had been working in before. So now I go to the long one, namely the partnership between Shanti and myself. This was in 1994, and so this was about 20 years, you know. This was, 1992 is when I took up this job, and this was up to 77. So it was 15 years that we did a lot of research together and had lots of fun. So this was the coordinated Hikamarka radar and scintillation measurements at the magnetic equator. And this is the only Basu diagram that made into my Kelly's book. Both editions of his book contain this diagram. So this may look familiar. And what it tries to do is to show that the 3-meter irregularity plumes that you see here, this was 1977, 19th March. And And we had common volume scintillation measurements at 137 megahertz, the signal coming from GOES 1. And the scintillations and the radar backscatter began at the same time. And that was around, this is 75 degrees west time, and it began a little before 20 local time, okay? And so if you just read through this, that it established that the onset of spread F and the kilometer scale irregularities, because the Fresnel dimension is what creates scintillations, and for 137 megahertz, the Fresnel dimension is very close to a kilometer. They attain saturation amplitude simultaneously. Later in the evening, meter scale irregularities decay faster than kilometer scales, owing to scale length dependent cross field diffusion. And this confirmed Gerhard Herendale's theory of equatorial spread F. It was an unpublished manuscript, never needed to get published. It became so famous the way it was, that mother and daughter irregularities attain maturity at the same time because the growth rate of smaller irregularities is faster. So you have them coming up at the same time, but at the end of the backscatter regime, I mean that's midnight, because the background density also decays and so forth. But there's enough background density and irregularity amplitude to have fairly high scintillation, not fairly high, but high scintillation at the end of it. And then you have this drifted structure which comes in, which has almost nothing except this little fuzzy thing associated with it. So you can use that to track scintillations in the beginning, but not at the end of the night at the equator. This is, of course, Hikamarka, and we have lots of Hikamarka specialists here. And then these are the other stations used by AFRL to study the strength of the irregularities at different parts of the equatorial region. So the first day cover, I just found it, which is kind of nice. I'm sure Shanti must have brought it home, because I haven't been to Ascension Island, but it really is a tiny piece of land in the southern Atlantic Ocean. It's a British protectorate, but it also has one of the most strongly turbulent ionospheres. So since the mid-70s, AFRL has used this ground station as the test bed for studying the robustness of communication receivers and navigation systems, not just communication, but also navigation. The multi-frequency scintillation input allowed the development of user-oriented scintillation models. And as I showed you, that we had several campaigns at Hikamarka to study the initiation of equatorial plasma turbulence. And it was started in the mid-70s. And some measurements were also made. Well, this is Hikamarka, that's Ascension. And this is the 46 meter, perhaps, or whatever, the fully steerable, yes, 46 meter dish at UHF, at VHF, UHF, to measure. That's primarily to look at backscatter and to look at, reflections from objects. So objects such as satellites. And so they're used for space surveillance. This is quiet time space weather. That's an intense scintillation event at Ascension Island. Under solar maximum conditions, 20 decibel signal fadings at 1.5 gigahertz, which is in the GPS frequency band. We used Merisat for this multi-frequency observation, but the higher frequency is very close to the GPS band, so that these values are applicable then to GPS. and 6 dB fadings at 4 gigahertz. And they're routinely encountered at places like Ascension Island. The voice communication becomes choppy and GPS position errors become unacceptable. So this was very kind of user-oriented, so we published it in IEEE, and this is, I think, for special areas in communication. And the AFSATCOM system provides critical satellite communication support to the civilian community and military. This is the AFSATCOM system has satellites in the Molniya orbit, and so for those have 12-hour orbital periods, and they hang over the high latitudes for a significant part of the day. And so even though you're going to higher latitudes, you don't have to wait, we're doing 15 minutes, okay. So also I got this statement from the chief of the AFSATCOM Systems Division, because we wanted, I think this is in our executive summary of our space weather report that NSF came up with. This is the first thing we wrote. And so he said that we're learning that space weather can have a significant effect on our communications. We must provide either reliable communications or at least a forecast of when there will be disruptions. So we were very happy to get that kind of a statement in our space weather report. So I have to move on. And this is the polar cap VHF scintillation variation with solar cycle, and that's the sunspot number. And from 1979 to 1986, so that's at least half of a sunspot cycle. And you see and these are the different dB values of the scintillation index, and you see the tremendous dependence of the scintillations on the sunspot cycle. And Jules Ahrens had started the measurements when he was still at AFRL, and we continued that. He left in 1981, and then we continued the measurements to try to see what happens through the entire solar cycle, because we also wanted to do a global map of scintillations. I'll skip that. That's a very interesting work we did with the Utah State group. But the third, so there's the equatorial belt, there's the polar cap, and then there's the polar cusp. And so this is experiments in the dark cusp. So neolescent at the day-side cusp. Now, actually, the day-side cusp is also in Sonderstrom, but the problem with Sonderstrom is that you have light during noon. But here, that is in the European sector, you have a dark cusp. So you have, at noon, you have total darkness. So, we went on a 2-week campaign and obtained good data and left instruments there. And anyway, forget about polar bears. I can just see Shanti with a gun. But if you get to go to New Orleans and you get one of these certificates that this guy has visited the world's northernmost community. So this is even higher latitude than Thule, Greenland. Thule, Greenland is, of course, the polar, come on, I'm getting stuck. What is Thule? No, thank you. But I'm saying it's the pole, magnetic pole, okay. Now because Rich tried for a long time to convince people that Thule is the magnetic pole and you don't have it in Alaska. So anyway, that's another long story. So this is now a kind of a totally a visual picture of after dusk you have the bubbles, the plasma depletions occurring, and these are the Appleton anomaly peaks. And so this is showing it in the US side, and there you see the convection is getting in through the polar cusp, and but that's in daylight, because I said in Sonderstrom you have it in daylight, and you see the polar cap patches and the auroral irregularities. So from all these measurements that we did a global morphology of scintillations. From that, we did a somewhat more, I get stuck with words these days, but it's less visual and more, gives you some dB numbers. So, and you see that during the very high sunspot condition, you have 20 dB scintillation on either side of the equator, and then this entire region is see, this is 18 UT, so I hope you've noticed that. And you also have auroral and polar scintillations, and that's supposed to be a sun-aligned arc, and these are supposed to be patches. And this is the much greater reduction of all the scintillations at solar minimum. So this is the scintillation world according to the Basus. Okay, and so, wow, should I go into this? But maybe I should. Controlled excitation of plasma processes in the middle latitude ionosphere by high power HF radio waves. I think the heater was on the dish, so we had no separate heating facility. But no, it was the heating facility was at Isloti. So that's in September 1981. I take that back. Well, in March 1980, we worked at Platteville, and we had both scintillations from space and ground because we wanted to do underdense and overdense heating for the proposed solar power satellite. Then we moved on to Arecibo, and we did radar backscatter and heater scintillation. And I don't know if Anthea is here, but Anthea is talking to and not paying attention. And I'm talking about her. And talking to Jonathan, my God. Okay. So anyhow, Anthea did the measurements from Guadeloupe, right? Isn't that true? Yeah. She was working on her thesis. So, you know, I mean, our lives have been entwined with so many people here in the audience. And we couldn't have done things without, and this is our only paper with Bill Gordon as a co-author. So anyhow, and this shows the scintillations at 430 megahertz. We could barely do any scintillations. But anyway, it was good enough, the measurements were good enough because it was done with the big radar, that you could still do the spectra with different amounts of heater power. And then finally, we ended up at ISCAT, where we made measurements in 1984 and 1992. So all these places, I've been there personally. And so this is how, so I was talking about these satellites with 12-hour orbits. So this is the kind of sub-ionospheric paths that they have over several hours. And you have to set up a station to get this within the heater power, within the heater beam width. And so you kind of back propagate and see where the station has to be. And the station turned out to be Grandfjord in Norway to do the ionospheric modifications. And this is the satellite, the scintillations from the transmissions of the satellite at on and off periods. And Shanti and Bob Livingston, which again, I'm sure lots of people here know Bob, they were in the field. And this looked so awfully barren and all that. Then I later found that these two ladies were running the inn, and I'm sure it made things more interesting. This lady, Anita Richardson, she really became a close friend of the family, and Shanti took a sari for her the next time he went there. So anyhow, then came Desert Storm. That was supposed to have been the good Iraq war, if you recall, under the senior Bush. And anyway, so Shanti had prepared a small booklet to give to the operators in the field to tell them about scintillations. So Shanti alerted his friend at the Strategic Air Command that equatorial scintillations will impact theater communication. And he told them about what were the statistics, and this information helped the Air Force to efficiently prioritize the satellite communication links during scintillation events. And so after the war, and because his booklet had come in so helpful, the AFSATCOM person prepared this little gift for Shanti to thank him for his expanding our knowledge of UHF satellite communication. So, okay, we've finished with phase one. We've come to the NSF decade. We're making progress. So what led to Shananda considering a position at NSF? You know, Dr. Ahrens was very upset that I was going into administration. Yeah, he was, yes. He thought I was a great scientist. Anyway, so that's the NSF building, for those who haven't seen it. The main thing is it's across the street from where I live. So it was very easy for me to put in long hours at work, okay? But that's ahead of the game. So what led to my considering it? The biggest draw, I think, was this membership in the advisory committee, because it was for atmospheric sciences. And to the NSF, this is going to mean a big difference than the GeoCAS or whatever you have now. But here, we were just advisory committee to the Atmospheric Sciences Division. So what we talked about made a lot of sense, because it was all in atmospheric sciences, and it was really great. And Mario Molina was one of my advisory committee members. I mean, that's exciting. So anyhow, I was there for some quirk. It should be a 3-year term, but it became a 4-year term. And then I led the CEDAR high latitude plasma structure group for many, many years, until Cesar and Jan Soika took over from me. When I joined NSF, of course, I had to give up any particular group. And then we organized the CEDAR Helps. I mean, how could you come up with a better acronym? And GAPS is Global Aspects of Plasma Structures. So it was the SCO-STEP group which made this conference international. And actually, Bill Wright, who's in the audience, he took me to Lyons, Colorado to hunt for Peaceful Valley, and this was a perfect place to have the workshop. And then, of course, there was the challenge of becoming the first woman to direct the aeronomy program. And since in the last 10 years, there have been 3 other women who followed me to that position. So I'm really pleased that finally the doors are opened. So I was the aeronomy program director for these 10 years. And as luck would have it, Bob Robinson and I joined together. There's Bob. So that could anything be more, fun and all that. So, well, so this is just FY94, and perhaps you can find your favorite PI on this list. But we were having coffee in Bob's office and decided that we were making finer and finer portions of the CEDAR pie. And was that why we have CEDAR? It has to be for other bigger things. So that year, we decided to go for the princely sum of 120K rather than 60K, which was the average size of a CEDAR grant. I don't know what it is now, but anyway, at that time, that was the story. And Wow. Good heavens. So I have to go fast. So anyhow, so that was the story of that. And oh, this one I have to show. This is, I was very, very sick. But Shanti went to the ISCA meeting, and there's Gerhard Herendel and Shanti and Michael with Mendilo with the beard. I don't remember that. But anyhow, the eye contact here is just something to see. And then, so I wasn't there. But here, I seem to be back in the saddle by 1996. And here's Don and myself, and this picture was taken by Shanti. And this was at the ERSI General Assembly in Lille, France in 1996. Well, as the US National Committee of ERSI, chair of Commission G, I nominated Don for the Appleton Prize, which he won. And I wrote an article on this in the CEDAR Post. I want you to know that's the difference between Distinguished Lecturer number 2 and Distinguished Lecturer number 3. I'm nowhere near Don in abilities, but I can write him up for a prize. That I can do. So, okay. So, as I said, I'm not going to get to the last phase, but here's the scientific initiatives at NSF that I did at that time. But now I find that the initiatives from what Anne-Marie showed yesterday, that they're getting larger and larger and NSF-wide, whereas this is something I did in the first two was just within aeronomy, and this was a way of bringing in money from the other groups, other agencies, whereas either it was just aeronomy or it was CEDAR and aeronomy together, such as in these three situations. So I'm saying our objectives were quite different than what is being done now, and you have to decide which is good and tell Rich. And of course the space weather is so successful, I won't even go into that. But then after I left NSF, I chaired SCOSTEP Climate and Weather of the Sun-Earth Systems program up from 2002 to 2006. And I presented 2 general lectures. Those were also 1 hour long. And so I've had some experience, I guess. And then and it was truly a successful program. And Germany, India, and Japan had national causes programs. And I have to show you this because obviously I didn't make it. But I went around the world for causes in 15 days in June 2004. So I first flew from Washington to Nagoya to open the Japanese program for causes. Then I went to Taipei to start off the workshop series for that region, or school, really a school. And then I changed planes at Singapore and went to Bangalore, where we had a very successful India-US conference. And then changing planes at Frankfurt, I stopped at home in Washington, D.C., and then immediately flew out to Santa Fe, where the CEDAR meeting was. So as you can see, this is not a fancy slide that I couldn't have made myself, and this is 38,000 kilometers. So Jonathan made this slide for me. And of course, while I'll just go through a couple of slides like this. While I was at NSF, Shanti wasn't sitting just quietly. He was doing research, and he and Keith developed the CINDA system, which has become extremely, extremely useful. And I wanted to talk about all these IHY sites in Africa, but I don't have time. But we've been able to really help the African community in space science, and I'm very proud of that. And then he was briefed, the military for CNOFs, and you all know much more about CNOFs now than I do even. And so, but the interesting thing is the original launch date was in 2003, when was somewhat of a sunspot maximum, you know, all the big storms we had. But actual launch was on April 16, and only our colleague Enda Woke pointed out to me that Shanti passed away on the 5th anniversary of the launch of CNOPS. So we've come, as I said, to the end of that, and I don't think I can do anything with this, but our current phase was working with magnetic storms, and I know that poor Dave is getting anxious. And I just have a few lessons learned for the students, only the students. And this is like my commencement speech, one view graph commencement speech for them. So, you know, you should have no regrets. Do the right thing by your family at the cost of your career, hopefully temporarily. You know, the fact that we went back to India. And we had a green card, but even went back because we thought that was the right thing to do. Anyway, follow your passion in the choice of your career. And not everyone gets things handed on a platter. Working through challenges strengthens your character. The guidance of mentors is essential, as I said. I wouldn't be here without them. High personal ethics is incredibly important. I mean, you should be taken on your word. No one should doubt what you are saying. And please remember that volunteerism is the backbone of our community. If people don't volunteer, then like Anne-Marie said, and I've also had a stint of 3 years at AGU on their board, and it's just very important. Without that, our community can't really foster. And I personally also feel very strongly that our science is so critically important to the environment around us that we have a special role to play in working on policy issues affecting it. So younger people, I hope some of you will choose that as a career, and that'll be, you know, like the Montreal protocol or other things like that, that can make a difference to the environment. And thank you very much. I think I'll stop there.